Hello everyone. In this lecture, we are going to discuss the mid-ordinate rule. And here, we are saying that the mid-ordinate rule is a numerical method used to approximate the area under a curve, similar to other methods like the trapezoidal rule or Simpson's rule. It is based on evaluating the function at the midpoints of subintervals and using those values to estimate the area under the curve. In other words, you can use it to estimate areas under a curve, area under curve, but also to evaluate integrals. Okay? So, like other methods such as Simpson's rule and trapezium or trapezoidal rule, we are able to estimate or approximate area under a curve or evaluate integrals. The only difference is that the other side, as we are taking the whole subinterval, here we are talking about the midpoint of the subinterval. So the mid-ordinate rule, as we use it, the integral of a function f of x over an interval a to b is approximated by dividing the interval into n equal subintervals, finding the function value at the midpoint of each subinterval, and then summing up the areas of the rectangles formed using these midpoints. So to make this simple, we have an integral of f of x with respect to x from a to b. Okay, the interval is a to b. We want to divide it into n subintervals. Therefore, the width of each subinterval will be b minus a out of n, and then this will be the area or the integral of this function over these intervals. And this is going to be h times sum of f of x, okay, I minus 1 plus xi, then divide by 2 from I is equal to 1 up to n. And these points are going to be telling you that here, if you have, for example, x naught, x1, x2, x3, okay? Now, we are going to be getting x naught plus x1, x naught plus x1, we divide it by 2. Then we substitute this value into function f of x, and we will have gotten y naught. Then we go ahead and get x1 plus x2 divided by 2, we will have gotten y1. We go ahead, x2 plus x3 divided by 2 will get y2, and move up to the moment we reach up to yn. And from that moment, then we shall be able to use the integral from a to b of f of x with respect to x approximately equal to h into y naught plus y1 plus y2 plus dash dash plus yn. And this will give us this integral of the function. So here, of course, we are trying to explain that xi minus 1 plus xi divided by 2 is the midpoint of the ith interval. So if we look at this is the first interval from x0 to x1, then its midpoint is going to be x0 plus x1 divided by 2. And we substitute this value into the function and get the value of the function at this midpoint. Then we proceed with others until we finish the whole interval, and then we sum the sum of those ordinates, the y naught, y1, y2 up to yn. We multiply it by h, which is the width of each subinterval. We'll be able to get what we call the approximate integral of that function. In other words, we are looking at a function f of x, which could be maybe parabolic in nature. So if it is like that, remember this is f of x, this is x. And we are going to look for we are going to estimate the integral of this function from maybe x naught to maybe, let me say, xn. Okay, so here we divide it into a number of subintervals. Let us assume that we have these subintervals. So for that matter, we are going to look at each of these subintervals and we look for the midpoint. So now, at those midpoints, this is where we are going to have the value of the function f of x being y0, y1, y2 up to the end. So why do we find that the mid-ordinate is also a good method to approximate area under a curve or to approximate an integral? It's because if we come here and draw this into rectangles, you'll find that the area which remains outside the curve is approximately equal to the area which remains inside the curve, and therefore the two can cancel each other during the moment when we are summing up these areas. I also continue, do the same with that, do the same with that, do the same with that, the same with that, okay, and the same with this. So I find that I'm actually using area of a rectangle, which is area equal to length times width. Length times width, I'm meaning if from here to here is the width, then this up to there is the length. So meaning that area, for example, area A1 would be from here to there will be y0. I multiply by the width from here to there, and that would be this x0. Okay, this is going to be x0 up to x1, so into h. Then area A2 will be y1 times h. Area A3 will be y2 times h, or maybe I call this A0, I call this A1, I call this A2, just for uniformity purposes. So meaning at the end of the day, I'm going to have area equal to A0 plus A1 plus A2 plus AN, and that would mean your area, or if we are talking about integral from a to b, f of x with respect to x will approximate to that area, and will approximate therefore to h into y1 y0 plus y1 plus y2 plus up to yn, and that will give you the approximate area of approximate area, which is equivalent to the area under this curve between the x-axis at lines x0 up to xn, or at lines x is equal to a up to x is equal to b. So that's how you can estimate the approximate integral or area under a curve using the mid-ordinate rule. Just a quick example, if we are integrating x squared, okay, from 0 to 2, we can divide, if we assume that our h is, for example, equal to 1. Now, if we take our h to be 1, that means we have 0, over this interval, we have 0 to 1 to 2. We look for the midpoints of these points. So midpoint of 0 and 1 will give you 0.5. Midpoint of 1 and 2 will be 1.5, because this is 3 divided by 2, and this gives you 1.5. So what we do, we use the 0.5 and 1.5, we substitute it in y, which is the function of x. And the function of x, okay, f of x equal to y is equal to x squared. So now we are going to be looking for y naught, which is f of 0.5. And this is 0.25 because we are saying this is 0.5 squared. Then y1 will be f of 1.5. So this is the same as 1.5 squared, and this is 2.25. So from there, obviously, the integral from 0 to 2 of x squared with respect to x will give us what? Will give us h, which is 1, okay? Because we took it to be 1. Then 0.25 plus 2.25. And finally, our answer will be approximately, this is approximately 2.5. So if we want to get a more accurate answer or a more accurate value, please use a smaller value of h, reduce h, maybe take it to 0.5, maybe take it to 0.3, maybe take it to 0.2. Then you look for the values of the midpoints over maybe the ordinates or the subintervals that you're going to take. If, for example, you want to use maybe 10 subintervals, then obviously this is going to be giving you a more accurate value than using only, here we use the only, I think we use the only two. We use the only two subintervals. So you can see the value is less accurate because when you integrate this x squared with respect to x, you find that it is equal to x cubed out of 3. So over the interval from 0 to 2, it approximates to 2.67, which is slightly higher than the 2.5. So for that matter, you need to have more subintervals and also a very smaller value of h, and then you will be getting closer to the more accurate value. So that's how we can use the mid-ordinate rule. So it gives an approximation of this, which is close to the exact value, but you can see it is less accurate than the Simpson's rule, but still useful for certain applications. Let's meet in the next video and be able to look at more detailed examples. Thank you.